Universal knot carriers and their relation to universal templates. Consider a compact, embedded, finite, two-dimensional branched object in 3 space. In the motivating example, it is built from 4 surface sheets, glued along a finite seam graph. So topologically, it is closer to a compact branched 2 complex than to a smooth embedded surface. For this question, no additional metric, orbifold, or analytic structure is used. Here is the motivating object itself, with a closed curve running along its sheets and passing through the seam graph. Now fix a specified class of admissible closed curves on the object. For example, these may be piecewise smooth closed curves, which run along the sheets and pass through the seam graph according to a fixed, finite set of local transition rules. Since the object sits inside 3 space, every embedded admissible curve determines an ordinary tame knot or link. This gives a forgetful map, sending each admissible curve to its knot or link isotopy class. Call the object a universal knot carrier if the forgetful map is surjective. Equivalently, for every tame knot or linked type, there exists an admissible, embedded, closed curve on the object whose image in 3 space represents that type. This is reminiscent of the Berman, Williams, and Grist theory of templates, where an embedded branched 2 manifold equipped with a semi-flow carries closed periodic orbits. A universal template is one whose closed orbits contain representatives of all knot and link types. Here, however, the admissible curves are not assumed to arise as periodic orbits of a semi-flow. The object is used first as a finite spatial carrier for classical knots. Any semi-flow would be additional structure. One route to proving universality is to show that admissible curves on the object can realize closures of arbitrary braid words. Then, by Alexander's theorem, every tame knot or link type should occur as the image of some admissible curve. So the question is this object a universal knot carrier?